Good morning everyone. I, Dr. Asha Bharati S, Associate Professor from the Department of Electronics and Communication Engineering, Jyoti Institute of Technology, extend a warm welcome to each and every one of you on the second day of the conference, Interdisciplinary Approaches in Civil Engineering for Sustainable Development. Today we are honored to have two distinguished keynote speakers from NITK Surathkal, Dr. Anupama and Dr. Mithun Mohan. It gives me great pleasure to welcome both of them to our conference. Welcome, madam. Now I invite Mrs. Bhargavi, Assistant Professor from the Department of Electronics and Communication Engineering, Jyoti Institute of Technology, to introduce Dr. Anupama to the gathering. Welcome, madam.
Good morning to each and everyone present here. Respected Dr. Chandrasekhar sir, keynote speaker Dr. Anupama ma'am, faculty members and my dear students. So it gives me an immense pleasure and honor to introduce our keynote speaker Dr. Anupama S. ma'am. Dr. Anupama S is an assistant professor of civil engineering at the National Institute of Technology, Karnataka, Surathkal. Anupama holds a PhD in Environmental Engineering from the Indian Institute of Technology, Madras, where she has worked on development of sustainable water treatment technologies using visible light active photocatalytic reactors for emerging contaminant removal. Her research focuses on the design, development and performance evaluation of low-cost water treatment technologies, circular economy and upscaling of solar photoreactors. Her research includes advanced oxidation process for water and wastewater treatment, physiochemical treatment of water and wastewater. She has been supervising 3 ongoing PhD projects at NITK Surathkal. She has published various papers in national and international journals and conferences and has 1 book chapter. Now, it's a pleasure for me to welcome our keynote speaker, Dr. Anupama ma'am, to deliver a talk on sustainable water treatment technologies. Welcome.
Good morning to one and all, and thank you, madam, for the kind introduction. Okay, so now my area of research lies on water treatment, and I've been focusing on some sustainable treatment technology, mainly focusing on advanced oxidation processes, in that photocatalysis. So here I will be just briefly talking about how photocatalysis can be a sustainable treatment technology. So what can we do, or what are the research involved in it to again bring it back to sustainable treatment technology. So when you talk about water, so water is a basic human right. Again, now when you have the UN Sustainable Development Goal, this is the 6th goal, that is your clean water and sanitation. So as it states, water sustains life, but safe, clean drinking water defines civilization. So the UN classification, as per UN classification, the annual water availability, if your annual water availability per capita is less than 1700 cubic meters per person, it is categorized as a water stressed region. So now we take India. India, the water availability annually is less than 1700 meter cube per person. It is 1486 meter cube per person. So India is a water stressed region. So now when you look into sustainability, so sustainability is we using our resources now without compromising or without sacrificing it for the future generation. So the future generation should also be able to use these resources. Okay, so sustainability, when you talk about sustainability, we have environmental, economical and social sustainability. So when you have a sustainable water treatment technology, that an environmentally sustainable water treatment technology, it will have to meet both the social and economical sustainability. So an environmentally sustainable water treatment technology will be one which will not be using excess of chemicals in it, and it does not need huge energy investment in it. So that makes it economical, and also you can produce water at a very economical rate or cheaper cost. So that maintains your social sustainability. So when you talk about clean water, so clean drinking water, so initially all our conventional treatment plants have been designed and have been perfected to remove the criteria pollutants. So the criteria pollutants, as we all know, the BOD, COD, turbidity, again biological parameters. So we have been perfecting our conventional treatment technology to remove all these criteria pollutants. But then again, when our analytical facilities have improved, in the 90s there came a new class of pollutants. So those are the emerging contaminants as we classify it. So these are contaminants which were present in the environment, but we did not have the instrumentation facility to analyze these. So once we started analyzing this, so we have these emerging contaminants which will include a lot of drugs in it. So now it has many endocrine disrupting compounds. Okay, so all these personal care products, daily personal care products, so all these what we use, it again gets washed away to the water. So the same water we treat and we use it. So the conventional treatment processes are focusing on removing of criteria pollutants. They were not designed to remove these micropollutants. So they are present in nanograms to micrograms per liter. So now when you take, for example, pharmaceutical, the presence of drugs. So this is an emerging contaminant. So pharmaceuticals, you might be aware of pharmaceuticals. So again, when you have a fever, you just might not wait for a doctor's prescription. You can just go on to the counter, tell, okay, I have a fever or I have a cough. You take a tablet for that. And most of the times, we take it without prescription. So over-the-counter attraction here in many of the developing countries is very high. So and moreover, the medicines you use, there will be a large part of it which is unused. So these also get, again, so what do we do to these medications which are left over? So these are all washed away, flushed, and these eventually end up in your wastewater treatment plants. So these wastewater treatment plants are conventional treatment plants. They remove the criteria pollutants, and most of the micropollutants which are present in this wastewater, they escape these wastewater treatment plants. Again you treat, now your effluent is having a lot of emerging contaminants in it, but we are discharging it off to surface water. We don't have certain guidelines as to what should be the concentration of many of these micropollutants. So they move on to the surface water. So surface water, so many of these compounds, these are drugs. They are active in very small concentrations. So you have many endocrine disrupting compounds, many drugs which affect the reproductive cycle. So you can see it has started affecting the ecosystem. So many of these microorganisms, again fishes, feminization of male fishes, hind legs in frogs. Okay, so again in India, during India and Pakistan late around 90s, they started banning diclofenac. Diclofenac was used as a veterinary, it was used in veterinary field as a drug. It is an anti-inflammatory drug. So this what happens is what's the vultures which were feeding on the carcasses of these animals started declining. So that is the effect these have on these drugs. Okay, so slowly they started banning the use of these drugs in veterinary use, but it is still being used for many of our medications. So if you take the drugs found in, so early 90s they started the research, and they have been reporting many presence of these drugs throughout the world in many of these surface waters, and they have also been reported in drinking water. So yes, this is just a comic. So once you go to, if you need a glass of water, you probably will be consuming a large amount of drugs along with it. Okay, so even though these are in nanograms or micrograms per liter, they are highly effective. So if you take a parent compound, so if you have, see these are anti-inflammatory, I'll be just skipping through these. So now you have different classes of drugs. So all these drugs, once we take it, so say diclofenac, so we are taking it, but the parent compound, 65% of the parent compound is excreted as such. Okay, so all this end up in your wastewater treatment plant. So now the conventional treatment plants are not equipped to remove these. So this is a data on the percentage removal using our conventional processes. So So many of these compounds like carbamazepine, diclofenac, brufen, their removal in conventional treatment processes are much less. So these are data of different compounds and their treatment processes, that is your conventional treatment processes is activated sludge processes, biological filter and its removal efficiency. So it has also been reported in many of the water treatment plants in India too. Okay, so these are few of the studies which have reported the presence of these pharmaceuticals in effluent. So now we have various removal mechanisms for this. Okay, so you have biodegradation, a process, much economical one, membrane filtration, UBH2O2, ozonation, again photocatalysis. Okay, so now all these treatment technology, even including photocatalysis, have certain limitations. So biodegradation, biological processes, the conventional treatment processes. Now what we have is many of these compounds have a very high half-life period. So their removal will take a longer period of time. That means you will have to have a very large treatment units. Okay, so many of this half-life period is in terms of days. Okay, so now membrane filtration. So membrane filtration is here you have a phase separation. So you are removing your drugs using membrane. So now what happens here is your drugs are stuck in these membranes. It is in the pores. It is not getting degraded, but it is not passing through the liquid. So again, the disposal of these membranes and this drug is still a problem. So UBH2O2, ozonation. So these are also promising technologies. Again, the cost of these are high. So you have to provide excess of chemicals, or you will have to provide energy for these UV lamp source. Ozonation, again, you have to provide ozone. So photocatalysis, here what we do is, here we have a catalyst. So this catalyst becomes active in light. So here it is an advanced oxidation process, that is you are utilizing your hydroxyl radical for oxidizing these drugs. Okay, so this hydroxyl radical, it has a very high oxidation potential of 2.8. Okay, so now this is helping in oxidizing your micropollutants which are present in your wastewater. So when you take a photocatalyst, so photocatalysis, here we will be using many types of semiconductors, TiO2, ZnO, RS, few of the examples. So if you take TiO2, the band gap energy of TiO2 is quite high. Okay, so for an electron hole pair generation to take place, it has to have a light source, a UV light source. So that is the amount of energy you have to provide. So now here what we are trying to do is to try to reduce the band gap so as there happens a redshift, so that you can utilize visible light and then help in excitation of these electrons. So here electron hole pair generation takes place and you will be able to generate a hydroxyl radical which we are interested in, and this will help us in removal of many of these pollutants. So again, please, these are not only used for micropollutants, these can remove all types of, again, your pathogens, removal of pathogens, these are non-selective. Okay, so now one of few advantages of photocatalysis is it produces less or no sludge at all, so secondary pollution is less. So we are aiming to mineralize your pollutant. So eventually getting converted to CO2, H2O, mineral acids, etc. So now it utilizes abundant light energy, it is cost effective, these are easy to implement, and it is environmental friendly. So now we have various factors which affect photocatalysis. So one is the photocatalyst. So as we said, so when we have these, we have photocatalysts which are active in your UV region. So if we can make it to get active into the visible region, we will be able to capture more of the solar light, and we will be able to run the treatment process without an external source of energy. Okay, so there are many researches happening in this area. So you have photocatalyst, its composition, its morphology, again this is an important parameter. Then you have light, the irradiation time, its intensity, and reaction temperature, the concentration of again your pollutant and your catalyst, and pH. Okay, so these are few of the factors which affect, and its application, you can find its application in many of the wastewater treatment units, air purification, all the metrics, air, soil and water, you can find its application as pollutant abatement. Okay, so now when you take a photoreactor, so the major components of photoreactors are, so now we have to bring the light and the reactants together, and they have to have proper contact with the pollutants. Okay, so this selection of the reactor plays a very important role. So when you have a reactor, it has various components. So one is the light source, then your catalyst, then you have a reactor, pumps, valves, the control system, all to send in your water in. So now a general process methodology is, so you define your problem, you screen for the target compound which you want to treat. So again, you have various selection and optimization or analytical procedures which are being involved. So you select a catalyst, you optimize its synthesis procedure, you go in for characterization. Okay, so now once you go in for characterization and you have a catalyst, you have to run batch studies. So along with batch studies, you will optimize what are the different factors which affect these. And with that, you can have your continuous studies. Okay, so here what we have done, try to do is we have tried to dope carbon into DiO2, thereby reducing its band gap. So its band gap was reduced from 3.2 electron volt to around 2.9 electron volt. So during this time, what happened is it can absorb the visible light. So the reaction can take place in visible light. So here you have a standard photocatalytic reactor. So you will have a socket for lamp, and you will have a water jacket surrounding it so as to maintain the temperature, and you will have your water to be treated in your cylindrical vessel. So this will have this, to this you can add, again you can add your catalyst to it. So the method of addition of catalyst, it can either be suspended type or you can immobilize it onto the surface of your reactor. Okay, so those are also factors which affect the removal. So now we have done various optimization studies. So the various factors what we have discussed is light is an important factor. Again, concentration of pollutant is important. Okay, so concentration of catalyst. So we have varied the concentration of catalyst, keeping the pollutant concentration constant, and we have seen how the degradation efficiency varies. So after a certain point we can observe that. So here the catalyst concentration was varied from 50 mg to 350 mg per liter. So after a certain concentration, as catalyst concentration increases, yes, you have more surface area for the pollutant to come and sit onto it and then undergo degradation process. But after some time, it starts, your solution becomes more and more cloudy. So there will be agglomeration of these catalysts taking place, and again the light penetration reduces. So you have to have an optimum value where you can have maximum removal efficiency. So we have done few trials and we have varied the catalyst concentration, and around 250 mg per liter we have got a very good removal efficiency. So now when you see, so this case we have added the catalyst to the solution. So now this is a suspended system. Okay, so now when you have this in your treatment plan, the major problem is now you have to retrieve back your nano particles from your treatment unit. You can't send these water off. Again, you will have a costly phase separation process which has to be given. So in most of the cases we have gone for some immobilization of these onto certain beads. So many of the polymers have been used, alginate beads. Again, it is derived from seaweeds. So again the problem we encountered was they undergo some sort of degradation. Then we had polystyrene PVC beads, and then we tried with the MBBR media. So the MBBR media, the traditional, the conventional treatment process, we had the media and we tried coating these catalysts onto the surface of the media, and we have used a fluidized bed model so that your catalyst or your pollutant can come in contact with your catalyst. Okay, so so when you go in for a slurry type of system, so you're losing a large amount of surface area there. So we try to fluidize it and we try to use LED lights around it. So now this is active and visible region. So these LED strips were placed around the reactor. So that was a light source. And then we have gone for water treatment. And again, the next step is, so once you have done, we have to see its reusability. So we recovered it from the system. So these were now again coated onto the surface of the media. So they were easy to recover it back. So you rinse it, you dry it, and then you reuse it. So for around 6 cycles, we could find it to be effective. So now what we have been discussing about is our parent compound. So the parent compound is being removed. Yeah, and the analysis was done using HPLC. So now we have seen the parent compound being removed, but again we might have some of the intermediates which is being present. Okay, so now your parent compound has degraded. We have to make sure complete mineralization has taken place. Your bulletin has degraded. For that we have taken the help of LCMS. So we have taken samples at regular intervals, and you can see as they speak. So that is your parent compound. Your parent compound. The next stage, it is breaking down into smaller compounds. So eventually these break down into the smaller compounds, and the final step should be mineralization of these. So this was then we have gone in for proposing a pathway. So this is your diclofenac anti-inflammatory NSAID drug. So that is being degraded or mineralized. So when you have these characterization techniques, so when this treatment technology with photocatalysis, so you will have initial characterization to be carried out. Once you have your catalyst, synthesized catalyst, you have to go in for characterization. So you do SEM and TEM analysis. So yes, I forgot to discuss about the SEM analysis. We had SEM analysis there. So it was a 50 micrometer size, 50 nanometer size of particle. So BET analysis, it has given us a surface area. So it is 62 meter square per gram of surface area. Solid state UV visible spectrum analysis has given us the band gap, that is from TiO2 it's 3.2 electron volt, it has reduced to 2.9, that thereby there is a red shift, it can absorb more of your visible light radiation. So again XPS analysis was necessary. So this has substantiated the doping of carbon in TiO2, and mineralization again was confirmed by LCMS analysis. MS analysis has. So we'll go in for preliminary investigation. Your batch reactor, it was a pseudo first order reactions, and again now you have different parameters to optimize. So you can use any of this optimization techniques. So we have used Design Expert, and we have used a central composite design for the study and usability study. We could get a removal of around for 6 cycles. So now I'll just go through what are the few of the researchers we are focusing on. So it is just 2 minutes more. Okay. So here we are focusing on few of binary composites where we use graphene oxide and TiO2. This is active. So we have carried out studies under solar right now. So this is active in solar region. So you have to provide a parabolic reflector so that you can concentrate the maximum intensity of light into your reactor, and this was used for dye removal. Again, now to make it sustainable, so we have said sustainability, yes, you have to reduce the amount of chemicals which is being used in your synthesis procedure. So for that we have been trying to reduce this by use of green synthesis. So green synthesis is the fabrication of nanoparticles using plant extract. Now this plant extract will act as a capping agent, thereby reducing many of the chemicals which we use in our treatment process. Okay, so green synthesis, many of the advantages is, one is it minimizes the use of chemicals, consume less energy, that it does not generate many benign byproducts, cost effective, it's a simple technique, and it can be easily scaled up. Okay, so here we have been concentrating on green synthesis of ZnO-TiO2 for dye removal and magnetized Fe3O4 TiO2. So ZnO-TiO2 for dye removal, we have used hibiscus leaf and its extract. Again for this Moringa aurifera, it is a bioactive, it acts as a chelating agent and it as a stabilizing agent. So now here we are used, here you see it is a magnetic Fe3O TiO2. So once you use it for your treatment process, you can have a magnet which can separate out your catalyst from the solution. So you can see the magnetic Fe3O4 TiO2 composite in the solution, and when you keep a magnet to it, it can separate out from your water. Okay, so that is one. So their green synthesis, again the costly phase separation process can be reduced. So now when we talk, these were all lab scale studies. So again lab scale experimental studies, you will have to carry out a lot of experimental reactions, a lot of fabrication, a lot of money. So we have to scale it up, we have to have some optimization. So now we have started with some of the computational fluid dynamics process, so where we mathematically model it. So they model a reactor, they change the various parameters in it, and they try to get the maximum removal efficiency, keeping maximum removal efficiency as one of the criteria. They try to optimize the reactor design and then later on go in for fabrication. So this can also help in scaling up of your reactor. So most of this case, this reduces the system cost, design time, and improve the performance. And ANSYS Fluid is the most popular commercial CFD software packages, and this is being used for this project. So many CFD modeled annular photocatalytic reactor. So you have your light source in the middle and you have your water to be treated as surrounding it. So now once they design the reactor, they wanted to see how introducing a baffle will change the removal efficiency. So they have tried introducing a baffle into the system. So now your water is passing through one of the segment, it is going in, it is coming back through the next segment. So this is a 3 baffle system. So now when you want in lab studies, if you want to see the effect of these baffles, again you have to fabricate one with 3 baffle, 4, 5 baffles. So when you have these computational techniques, you can go in and you can try to study these with these software, you can optimize it, and once you are optimizing it, then you can go in for your fabrication process. So again, they have tried, so those were annular type of reactors. So again, when we discussed reactors, there were different types of reactors. That was an annular type of reactor. This is a flat plate type of a reactor. So they have, so to increase the flow path, that means it will have a more contact time with catalyst and the pollutant. They have gone in for serpentine flow path. Okay, so here you can see how the pollutant removal takes place, how long the pollutant removal, what is the HRT, so you can calculate those. And if you want to introduce baffle into the system, you can introduce a baffle and you can see what is the effect of these baffles, the number of baffles. Now again, the type of baffle, the inclination of these baffles, all can be studied. So we are looking into some of the circular, this is the last slide, stopping. So this is from a few circular economy concepts. Again, we are trying to, now sewage sludge management has been a bit difficult. So now we are we are using this sewage and then you are mixing with some of the agricultural waste, and we are trying to synthesize biochars which can be used as an adsorbent in removal of most of these pollutants. So one such studies, they have used this sewage sludge, mixed it with coconut shell, they have powdered it, they have mixed it, made a biochar out of it. They have gone for column studies and they have been successful in removal of many of these drugs. Yes, thank you.
Thank you, Dr. Anupama Madam, for gracing us with your presence and also sharing valuable insights into sustainable water treatment techniques. May I now request Dr. Chandrasekhar Sir, Professor and Head of the Department of Electronics and Communication Engineering, Jyoti Institute of Technology, to felicitate Dr. Anupama on behalf of our institute. Welcome.